Hi, this video is going to cover Chapter 5 for our introductory chemistry class. This chapter is called Molecules and Compounds, and our last chapter was Atoms and Elements, so we've now moved up. We're taking our atoms and elements and combining them to create molecules and compounds, and the majority of the time for this video will actually be spent learning how to name the compounds. So I have a feeling it's going to end up being a little bit longer of a video, and I highly recommend following along in your textbook so that you can do the practice problems when it comes to the naming of compounds. So we're going to start by talking about what happens when we combine atoms and elements to make molecules and compounds. Oh, that's my cat. Go on, kitty cat. So we're looking at two compounds here. One is table salt and the other is sugar. And when table salt is broken down into its elements, it's made of sodium and chlorine. Sodium is a metal. It's very reactive, it's explosive, it's poisonous. Chlorine is a gas, it's yellow, it's also poisonous, it's also stinky. But when we put these two together, we make sodium chloride, we make table salt, and it's white, it's salty, it's edible. It doesn't hold on to those previous properties. So when elements combine to create compounds, they gain new properties. They don't hold on to the previous properties they had as individual atoms. So we're going to add to our list of laws that we've talked about. We've done the law of conservation of energy and the law of conservation of mass. This is the law of constant compositions, and it says that any sample of a compound will have the same proportions. So we know that water is H2O, so we can think of this as a 2 hydrogen to 1 oxygen ratio, and that ratio is consistent regardless of where the water comes from. And the reason for this is because that when we have a compound, that compound is made up of many molecules of the same type. So a glass of water is made up of lots and lots of water molecules, all of which are H2O. Now that doesn't mean that H2O2 doesn't exist. It does. H2O2 is hydrogen peroxide. So when we add or remove elements, it's going to turn it into something else. And so now when we have that 2-to-2 ratio, it's going to have very different properties. Oh, one more thing before we move on. Let me go back over here. So I did say it was a 2-to-1 ratio, and this is based off of counting those atoms. We could also look at it based off of the mass. So if we have 2 hydrogens, that's 2 grams of hydrogen, and 1 oxygen is 16 grams of oxygen. So we could look at it as a 2-to-16 or 1-to-8 ratio based off of the mass. So that ratio could be a counting ratio or a mass ratio. So as we move into talking about the actual formulas for the compounds, there's a lot of information that goes into them. We have to have each of the elements listed that are in our compound using those chemical symbols that we talked about in the last video. And we need to know how many there are. So we're going to put the number of the atoms as subscripts to the right of each element. So if we have sodium sulfide, we would write it like this. That tells us that there are 2 sodiums and there's only 1 sulfur. We don't write the number 1. It's implied. So if an element doesn't have a number next to it, then we know that there's just one of them. The example on the bottom here is a little bit more complex because it's using what's called a polyatomic. So if we look at that word, polyatomic, poly means many, and atomic just is atoms. So a polyatomic is a group of atoms that share a charge. So in this case, our polyatomic is NO3 with a 1- charge, and this is called nitrate, and we'll talk more about our polyatomics in a few slides. But the formula that's here, right here in the middle of all these arrows, is MgNO32. So we have the symbol for magnesium, and it doesn't have a number next to it, so that means that there's just one magnesium. And then the NO3 is placed in parentheses with a 2 on the outside. So that means that there are 2 nitrate groups, or 2 NO3 groups. Altogether, there will be 2 nitrogens and 6 oxygens, because that 2 can get distributed throughout that polyatomic. But altogether, there are 2 NO3 groups. So a couple ways to look at it there. There's also a handful of ways to represent a structure. So there's a couple things on this slide we need to talk about. The first thing are those 2 words right there, empirical formula and molecular formula. The empirical formula is the lowest ratio. And the molecular formula is how it actually exists. So the first example there is benzene. Benzene's formula is C6H6. But if we reduce that down to the lowest possible ratio, it's a 1-to-1 ratio, or CH. And then we have 4 different ways really to write this out. The first one is that molecular formula. It's telling us how many atoms and what their ratio is. The second structure right here is the structural formula. It's showing us all of the bonds within that molecule. So the carbons are held together by bonds in a hexagon shape, and then they each have 1 hydrogen attached. And then the 2 others are computer models. So the first one's a ball and stick model. So really it's very similar to that structural formula. We've just replaced the atoms with, or the letters with spheres representing the atoms. And then that last one's called a space filling model. And this one's actually the most accurate, but it's also the most difficult to see because it can hide areas that we want to know about. Let's look at the bottom one on here, glucose. So the formula for glucose is C6H12O6, and all of that can be divided by 6. So our empirical formula is CH2O. And then we have our very long structure here for the structural formula, and that ball and stick model, and the space filling model. One more example I want to point out, if we have Na2SO3, that's our molecular formula. That's how it actually exists in nature. But it's also the empirical formula. It's already in its lowest possible ratio. So the sodium, sulfur, and oxygen are in a 2 to 1 to 3 ratio. So this is the molecular and the empirical. And I wanted to point that out just so that you know that the empirical can be the molecular formula. So we've divided our matter into pure substances and mixtures, and we divided our pure substances into elements and compounds. So this is really just a continuation of that chart. So we're going to divide our elements into atomic and molecular, and then we're going to divide our compounds into molecular and ionic. So we're going to start with just a quick definition of each one, and then we'll go into a little bit more details. The atomic, move my video over. The atomic elements are elements that exist as single atoms. So the example up here is mercury. So those are mercury atoms that are all together. So area up here is showing us the little tiny spheres representing the mercury atoms. Molecular elements are elements that form molecules. So these are two or more atoms of the same type. So here's our example. This is Cl2. Molecular compounds are compounds that are made up of nonmetals. So this is two or more different types, and it's specifically nonmetals. And our example over here, that is carbon dioxide, and that's CO2, or dry ice. And ionic compounds are compounds whose particles are cations and anions. So remember, that's a plus charge and a minus charge. And our metals like to form cations. So this is not the only way that it will exist, but a common way is to have a metal with a nonmetal. So we're going to dive a little bit deeper into a couple of these labels, and one of them is the molecular elements label. There are 7 elements that form what is called a diatomic. So again, if we look at that word, we know that di means 2. Atomic is really just saying atom. So it's saying that there's 2 atoms. So it's saying that these elements come in pairs. Now the way to remember which ones do this is based off of the rule of 7s. So there's 7 of them that do it. We find element number 7, which is nitrogen. We make a 7 by going down column number 7. So here's our starting point. There's element number 7. We find column number 7. We go down. We make a 7. So there's my 7. And then the last one is, don't forget about hydrogen. So hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine all exist as a diatomic element or a molecular element. Now there are other atoms that do this as well outside of the diatomic. S8 is one of them. So this is forming 8 sulfur atoms into one molecule. The ones that you need to remember are these 7 diatomics though. So a little bit more on the molecular compounds. The biggest thing to remember here is that we're going to have 2 or more different nonmetals. The smallest unit is a molecule. And then our ionic compounds, this is when we're going to have a cation and an anion, and very common for it to be a metal with a nonmetal, but there's other options, and we'll look at those in a few slides. And the smallest piece that we can have is a formula unit. So it's not a molecule, and this is something we'll talk about later on in future chapters, but we can just think of the term formula unit as a molecule for an ionic compound. It's really just the lowest ratio for that compound. So we're going to talk about how to write the formulas, and we're looking at how to write formulas for ionic compounds. The cation always comes first, and the anion always comes second. The goal is to create a neutral compound, and so we want to have a equal amount of positive and negative charge. And sometimes this can be easy to see. So our sodium is a 1 plus, our chlorine is a 1 minus. We put them together, we get NaCl. It's neutral because we have 1 positive, 1 negative. If we have a +1 with our sodium and a -2 with our sulfurs, then that means we're going to need 2 sodiums so that we can get those 2 pluses to balance out our 2 negative. So we get Na2S. If we have 2 pluses and 2 minuses, again, we just need 1 of each to balance it out. There's a a little trick if our numbers are a little bit more complicated. So we're going to look at calcium with nitrogen. Calcium forms a 2+ charge, and nitrogen forms a 3-. And this is something that we know from our last chapter because where they are at on the periodic table tells us their charges. Now, if I have a 2+ charge and a 3- charge, and I want to end up with a structure that's neutral, I have to think of what the least common multiple is between 2 and 3. So the least common multiple is 6. So that means I want to have 3 of these so that I'll have a 6+ charge, and I want to have 2 of these so I have a 6- charge. So I end up with Ca3N2. 3 times that 2+ charge gives us the 6+, and 2 times that 3- charge gives us the 6-. Now, there's a little shortcut to this though. I'm going to erase this. And I'm going to show you another way to do this exact same problem. If you take the number, not the positive or the negative, but just the number, and you cross them, this is often called the cross rule, that can become the subscript for the other element. So we got to the exact same conclusion that I just showed you, but I showed you why it works. 3 times that +2 gives us our +6, and 2 times that -3 gives us our -6. So the +6 and the -6 are neutralizing each other out. Now if you use the cross rule, the only catch is after you use the cross rule, you want to reduce the numbers if needed. So for example, with the magnesium and the sulfur over here, if we decided to just do the cross rule, we would get Mg2S2. We would want to reduce that down, divide everything by 2, so that we would just get Mgs. So the cross rule will work every single time as long as you're also reducing it. Now the same is true if we're using our polyatomics. Now on table 5.3 of your textbook, there is a list of polyatomics. In a couple slides, I'm going to tell you a very easy way, hopefully a very easy way to memorize them. There's a lot of them, so it's really not even memorizing them. It's just kind of a trick on how to use the periodic table to help you figure them out. But a polyatomic is a group of atoms that share a charge. So listed right here are some examples. So we have ClO with a 1- charge, SO3 with a 2- charge, NO3 with a 1- charge, but we're combining them together in the same way. So in that first example, we have a sodium with a 1+ and a ClO- with a 1-. So it is a 1-to-1 ratio. If we have an Na+ and an SO3 with a 2-, then we need to have those 2 sodiums to balance out that 2- charge. And if we have Mg2+ and NO3 with a 1-, we need to have 2 of those nitrates, 2 of those NO3s to balance out that magnesium charge. And if we have more than one polyatomic, we want to put it in parentheses. We're going to do one more of these. We're going to look at aluminum with carbonate, which is CO3 with a 2-. So aluminum has a 3+ charge. So this is very similar to our example on the last slide. We have the 3+ and the 2-. So I'm going to use my cross rule. So I know that I need 2 aluminums, and I know that I need 3 carbonates. So I'm going to put my carbonate in parentheses with the 3 on the outside, because we have to treat that as one group. It sticks together. And it's not a coincidence that the 3 and the 2 are what I also used on the last slide. Having a charge of 3 and 2 is really as complicated as it gets. So I'm trying to just show you the most complex type of example. All right. We've kind of reached the halfway point of our video. The second half of this video is going to look at how to name our compounds. We're going to have 3 sets of rules. The first set is for ionic compounds. The second set is for molecular or covalent compounds. And then the third set is for acids. And we are definitely starting with the most complex. When we name an ionic compound, just like in the formula, the cation gets listed first and the anion gets listed second. Now there are 3 types of cations: a type 1 metal, a type 2 metal, or a polyatomic. There's also 3 types of anions: a nonmetal, a polyatomic, or a polyatomic that has hydrogens added to it. So we're going to talk about each of the cation types and then each of the anion types, and then put them together. So starting with the cation types, the first type that was listed was a type 1 metal. These are metals that have a predictable charge. So we looked at our periodic table. We know that we can base our charge off of locations on the periodic table. Remember, we went across and said, here, let me grab my periodic table here. We went across and said +1, +2, +3, -3, -2, -1. As we go across our row there, those are the predictable charges that this is referring to. If we have a type 1 metal, its name is its name, meaning there's nothing to change. That's the easy one. If we have a type 2 metal, so these are mostly transition metals, but really it's any type of metal whose charge can be various things. We're still just going to use the name of the metal, but we're also going to put the charge of that metal in Roman numerals. Ionic compounds are combined together based off of those charges. We saw that when we were making them neutral, and so we need to know what that charge is since it can be more than one thing. So the examples over here, cobalt with a 2+ charge is cobalt 2. Lead with the 4+ charge is lead 4. So we have 1, 2, 3, 4, 5. We really don't go above 5 too much, but you should know those Roman numerals. They're going to come up a few times. And then the third type of cation is a polyatomic. There's only one positively charged polyatomic that you need to know. Here's its formula: NH4. It has a 1+ charge, and its name is ammonium. So if this is used, you're just going to use its name, which is ammonium. So there we go. For our cations, really, you're using the name of whatever it is, whether it's a metal or ammonium. And then if it falls into that middle category, those type 2 metals, you're also going to include its charge. So not horrible so far. Let's look at our anions. If we have a non-metal as our anion, we're going to use the name of the non-metal, but change its ending to "ide." There we go. My green didn't show up on the green. Very good. So the examples over here, nitrogen with a 3- charge becomes nitride. Chlorine with a 1- becomes chloride. Oxygen is oxide. So not a big change. We're just changing the ending to "ide." For the polyatomics, again, table 5.3 will give you some examples. More on the next slide. But really, it's just going to be the name of the polyatomic. The hard part here is knowing what the name is, and I'll show you that on the next slide to help you out. And then the last one is if we have a polyatomic with a hydrogen. If it just has one hydrogen, we're going to say hydrogen and then whatever the polyatomic's name is. So like HSO4-, SO4's name is sulfate and it has one hydrogen, so HSO4 is hydrogen sulfate. If it has 2 hydrogens, we just add di in the front to say that there's 2. So H2PO4-, PO4- is phosphate. So because it has those 2 hydrogens, we're going to call this dihydrogen phosphate. Okay, let's talk about these polyatomics a little bit more. Now, you've seen some examples of polyatomics on a couple slides here. And let me just put one up here as an example to get us, there we go, to get us started. CO3 2-. The name of this is carbonate. Polyatomics are also called oxyanions because they all contain oxygen and one other type of nonmetal, and anion because they're negatively charged. So when you're memorizing polyatomics, there's really three things you have to remember. You have to remember how many oxygens it has, what the charge is, and then how do we name it? And there's not a great pattern. So carbonate is CO3 2-, but sulfate is SO4 2-, and chlorate is ClO3-. So notice that even though they all have similar names, carbonate, sulfate, chlorate, there's not a consistency between their charges or their number of oxygens. So I'm going to erase all these so we don't get confused. The way that I like to teach this is called the T43 method. So I have part of a periodic table on my slide here, and I'm going to write in T43. There's the T. There's the 4. And there's the 3. Now, what this table helps us figure out is the number of oxygens and the charge of all of the 8s. Sorry about that. I think I hit a weird button. Okay. So this table is going to tell us the 8s: sulfate, phosphate, nitrate, carbonate. And how this table tells us that. Oh, goodness. I'm trying to pick a color that's too close to the other buttons. Here we go. So in that T section, the T stands for 3. And that tells us that each of these have 3 oxygens. So borate is BO3, carbonate is CO3, nitrate is NO3. Now, the other thing we need to know, though, is the charge. So as we go across, we have -3, -2, -1. The 4 tells us that these all have 4 oxygens. And again, for the charge, we're going to restart -3, -2, and I'm going to fill in my last charge, -1. So we're going to do 3, 2, 1, 3, 2, 1. So I'm going to fill in my charges here. I have -3, -3, and then -2s. And then the last row there, that 3 is also going to tell us that we have 3 oxygens. And everything in that column is a 1-. This can be a nice little cheat sheet to help you figure out the names of these polyatomics. Now, this isn't the full story, because maybe on a previous slide you saw that, well, it wasn't written as NO3, it was written as NO2, and it wasn't SO4, it was SO5. So remember I said that these are all of the 8s. We can change the number of oxygens and it will change the name. So here's sulfate. This is the one we saw on our last slide. If we add an oxygen, so now it's SO5, the name becomes persulfate. So here's our starting point. Here's 8. These are the names from the T43. If we add an oxygen, we add per to the front of that name. Now notice the charge doesn't change. Everything in this column here is a 2- charge. We're changing the number of oxygens and we're adjusting the name. If we remove an oxygen, so we go from SO4 to SO3, it becomes sulfite. And then if we remove one more oxygen from that, so now it's SO2, it becomes hyposulfite. So if we start from the bottom, from the least amount of oxygens, and work our way up to the most amount of oxygens, we go from hypoite to ite to 8 to per 8. So the two extremes, the least and the most, have the suffix in the front, the hypo or the per, and then the two in the middle don't have that. This is the most complicated, and it's not a difficult concept. It's just a lot of very detailed rules to follow. Whether or not you understand the chemistry here doesn't really matter. We're just looking at rules on how to name something. All right, the last type of anion, remember we had 3 anion types. We had nonmetals, and those just become ides, like oxide. We had polyatomics, and then our last category are polyatomics with hydrogens. So we add a hydrogen, the word hydrogen, to the front of the name, but this is also going to change the charge. Hydrogen's a +1, so we're going to take whatever the old charge was, and we're going to add a +1 to it. Now, here's our example. Phosphate is PO4 with a 3- charge. So when we add that hydrogen to the front of it, that 3- charge is now a 2- charge, and it's HPO4. Dihydrogen phosphate now gets 2 hydrogens, so that charge goes down by 1 even more. So it's now a -1 charge. All right, let's put all this information together. So we have CaCl2. So our cation is right there. That is a type 1 metal, meaning we know its charge. So all I need to write down is calcium. That's the name of my cation. My anion is a nonmetal. So I know that it is chlorine, but I'm going to change its ending to chloride. So there's my cation, and my anion, the name of that compound, is calcium chloride. So definitely started with an easy one for us. So what about the next one? Fe. We know Fe is iron. But I also know that iron is one of my transition metals. So I know that I'm going to need to put its charge in brackets there. So I'll leave that open for a second. NO3. So if we go back to our table and look at where NO3 is, NO3 is one of our 8s. It's one of the originals. So I know that NO3 is nitrate, and I know that it has a 1- charge. Now, we don't really care about the charge on nitrate, but we do care about the charge on iron. So because the charge on our type 2 metals can vary, we need to state what it is. And we have to figure that out from the other elements or polyatomics in the compound. So nitrate has a 1- charge, but there's 3 of them. So altogether there's a 3- charge. Iron needs to balance that out. So that means that iron is a +3 charge. All right, next example. We're starting with Mg, magnesium. Magnesium is one of our type 1 metals. So all I need to do is write down its name. And then we have BrO4. So we know it's in the bromine family. If we remember where bromine is, it's over here in the 3 section. So BrO3 is bromate. So if we know that BrO3 is bromate, and we've added an oxygen to it, then that means that this guy has to be perbromate. So we were right here, we knew that our bromine had the number of oxygens based off of our T43, but it had that 1 extra oxygen. It went from BrO3 to BrO4, and so we needed to add the per in the front of its name. And then our last example, we have a type 2 metal. So I'm going to write its name, chromium. I'm going to leave a little blank there to put in its charge. And then we have HCO2. So this is our polyatomic with a hydrogen. So I know I'm going to put the word hydrogen. And then I need the name of that polyatomic, CO2. CO3 is carbonate. So if CO3 is carbonate, and I'm going to remove an oxygen to make it into CO2, that means CO2 is carbonite. So CO3 is carbonate. We remove an oxygen to get us to CO2, and that makes it carbonite. So then we have to talk about what charge goes into those parentheses. CO2 is a 2-, and I know this from here, right here. CO3 is a 2-, so that means CO2 is also a 2-. Hydrogen's a 1+, so we put those together, and they are a 1- altogether. So this is a 1-, which means that chromium has to be a 1+ to balance it out. So in my brackets here, I'm just going to put a Roman numeral 1. And the way we would say that is chromium 1 hydrogen carbonite. We actually do say the numbers. All right. We just went through the most complex naming style. We're going to do the easiest one next, and then the middle one last. But I'm telling you this so that if you want to pause and go do some practice problems or rewind and rewatch some stuff, you know that this is a good pausing point. So now we're going to talk about molecular compounds. Molecular compounds are made up of nonmetals, and they can be made up of multiple nonmetals, but we're going to talk about how to name molecular compounds that are only made up of 2 types of nonmetals. And there's really not that many pieces to it. Molecular compounds aren't based off of charges, so we have to state how many of the nonmetals are there. And so we're going to use prefixes to do that. So we have a little box on the bottom here that tells us our prefixes. 1 is mono, 2 is di, 3 is tri, and so on. You probably have seen these in other classes, and if not, you're definitely going to see them in future classes. So we use a prefix to tell us how many of each nonmetal there are. The most metallic element goes first. So if we think about our periodic table, here's my periodic table. Here's my little stairs that divide the nonmetals and the metals. Whichever nonmetal is closest to those stairs, that's the one that's the most metallic. So another way to say most metallic is that we can say that it is closest to the stairs. If there's only one of that first nonmetal, we don't use the prefix mono. It just doesn't get a prefix at all. And we just use its name. We don't change it in any way. For the second nonmetal, again, we're going to use a prefix. It's going to be the one that's least metallic, so that's kind of a given. And we're going to change the ending to "ide." So just like we did for our ionic compounds. So if it's oxygen, it becomes oxide. So here's our examples. We have P4S10. So I know that my prefix for 4 is tetra. So tetra phosphorus. And I know my prefix for 10 is deca. Deca sulfide. So sulfur becomes sulfide. And then that next one we have N3O5. 3, my prefix is tri. So tri-nitrogen. And my prefix for 5 is penta. Oxide. So we're using our prefixes and "ide" on the second element. And that's it. We're done with the molecular. I think that took maybe 4 minutes. That's a quick one. All right, last naming category are the acids. And we do have 2 types of acids. We have binary acids and oxyacids. So binary acids are called bi because it's a hydrogen and then one other type of nonmetal. So it just contains 2 elements, hydrogen and then some other nonmetal. The way we name these, hydro, the name of the nonmetal, but we change the ending of it to "ic," and then the word acid. So here's our examples that are down here. HCl is hydrochloric acid. H2S is hydrosulfuric acid. So hydro in the front, acid at the end, and an "ic" in the middle. That's it. That's all there is for binary. It's a pretty quick one also. And then our last category are oxyacids. And oxyacid is a hydrogen with one of our polyatomics. And the name of the acid is going to be based off of the name of the polyatomic, specifically the ending. So we saw that our polyatomics, as we change their name, so thinking about the sulfate one that was on that slide, the most amount of oxygens was persulfate, then sulfate, then sulfite, then hyposulfite. So they were all ended in either ate or ite. If our polyatomic name ends in ate, then we change the ending to "ic" and throw the word acid on the end. If our polyatomic ends in ite, we change the ending to us, O-U-S, and again, add the word acid to the end. And the way that I remember this, I think actually one of the tutors I had in my class years and years ago taught this to me, but the way to remember it is that the white mouse ate icky cheese. So if your polyatomic ends with ite, you change it to us, and if it ends in ate, you change it to "ic." Again, it's silly, but you'll remember it. So let's put this to use. And we're going to do this with a lot of iodine examples. So we have HI. So this is a binary acid because it's just hydrogen and iodine. So I know it's going to start with hydro. And I know it's iodine, but I'm going to change the ending to ic. So it's going to be iotic. And then it will end with acid. So hydroiodic acid. And then we have HiO3, HiO4, HiO2, and HiO. So I'm going to go back to our T43 slide here. So if we look at where iodine is, IO3 is iodate. And that's really the most important piece of information to filling this in. So over here on the side, IO3 is iodate. And so that is our next one. We'll start there. So that means that if the white mouse ate icky cheese, 8 becomes ic. So this is iotic acid. Now notice how similar those two names are, hydroiodic acid and iodic acid. One of them doesn't have oxygens, one of them does, but very different names. HiO4, it has that extra oxygen on it. So we know the name of this is periodate. And so we're just going to change the ending to ic. Periodic acid. What about HiO2? IO2 is one less oxygen than our original, so this is iodite. So the ite becomes us, and this is iodous acid. And then HiO, so now we have 2 less oxygens from our original, so the name of this would be hypoiodite. And again, we're just going to change the ending there to hypoiodous acid. So using that T43 method, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12 nonmetals on this table. So that gets you to 12 polyatomics that end in 8. But using this, that gets you to 48 different polyatomic names, which means that there are 48 different oxyacids that you should be able to name. All right, that is the end of naming. We have one last topic in this chapter, and that is a formula mass. So there's a tiny bit of math in this chapter. We can't get through a chapter of chemistry without a little bit of math. And the formula mass is the mass of an individual molecule or formula unit. And so to calculate it, we're adding up all of the individual pieces. So we have a little equation down here on the bottom, but it says that the formula mass is equal to the number of the first element times that element's mass plus the number of the second element times that second element, and then ... because you keep going until you've used all the elements. The atomic mass is from the periodic table. So on my periodic table here, it is the numbers towards the bottom. So underneath calcium there, I know that's blurry. You don't really need to see what it says. But underneath the name of calcium, it has what the actual mass of calcium is. So you're using those values from your periodic table. So for example, for water, we would do 2 times the mass of the hydrogen, because there's 2 hydrogens, plus 16, and there's only 1 oxygen. So altogether, a molecule of water would weigh 18.02 AMUs. So remember, an AMU is an atomic mass unit. So a couple quick example practice problems. Calculate the formula mass of Fe2S3. So just to remember our name for this would be iron 3 sulfide, and I'm able to name that so quick because I did the cross rule in reverse. So I took that 3 and put it over there. So I know that my iron has a 3+ charge. So I can say iron 3 sulfide. It's a nice little trick to do there. All right, here's how we're going to do this. I'm going to erase this so we can see our numbers a little better. We're going to take the mass of iron times 2 plus the mass of sulfur times 3. So there's our numbers. That's the mass of iron. That's directly from my periodic table. That's the mass of the sulfur, again, directly from the periodic table. We multiply those together. Notice that my number of decimal places stays consistent as we do this. So I have 3 decimal places, and then I add them together, 207.885 AMUs. So what if we have a polyatomic? We have some parentheses. It doesn't change. So we're going to do the mass of magnesium times 1 plus the mass of nitrogen times 2 plus the mass of oxygen times 6. So remember, this 2 here gets distributed through those parentheses. So we end up with 2 nitrogens and 6 oxygens. So we have the mass of magnesium times 1, and I know that that's the same thing as it is times 1. I know that mathematically that doesn't change. I'm just putting it in there so you can see that I didn't forget to do it. And then we have the mass of nitrogen and the mass of oxygen. We get those numbers, we add them together, and we get the mass is 148.313 AMUs. Now, depending on what periodic table you're going to use, you might get a different number of decimal places. So, especially if you're looking at ones online or if you downloaded a periodic table app on your phone, try and use one that has 3 decimal places at least. That's going to give you more accurate results. And I will try and find, I will find a periodic table PDF that I will post on Canvas for everybody so that we have one that we can use consistently together. All right, that is it for our Chapter 5 video. Thanks for sticking with me. I know this was a long one.